where the hormones are secreted from some nuclei or some areas, some cells in the hypothalamus, mainly the cells around the optic chiasma, the para-optic area, or the optic, where the cruciate or the cross, the junction of the optic nerves are, and this is called the optic chiasma. And so these are usually supraoptic, para-optic areas. As you can see, a lot of the secretions are from that area, and others are just from somewhere next on the right side, the arcuate area. The arcuate area of the hypothalamus, and then we have the whole of that mammillary body, mammillary area, and all these areas secrete hormones, they secrete chemicals into the anterior pituitary. But what is most significant about it is that these hormones do not go into circulation, into the systemic circulation, to go from hypothalamus to anterior pituitary. They have a shunt, they have a direct pass from hypothalamus into anterior pituitary, what is called a portal shunt or a portal system, a hypothalamo-hypophyseal portal system or portal blood system of something like venules, large veins that drain the blood straight into the pituitary. This is one of the very few portal veins in the blood, in the body, where blood flows directly from one area into another without having to circulate through the heart. You remember we have the hepatic portal vein in the embryo or in the fetus, and again there is such a portal system around in the testes. These are the only 3 portal veins, or the only 3 shunts of blood that we have. And the most important is this one, from hypothalamus to anterior pituitary is direct secretion into some blood vascular system that takes it directly into anterior pituitary. Hormones are these that are secreted from hypothalamus into anterior pituitary. And we already said there are 2 groups of hormones. One is the peptide hormones, growth hormone, ACTH and prolactin, and the other one are the glycopeptides. They are peptide hormones with a glyco or with a carbohydrate moiety, makes them more soluble for transport and covers their receptors in such a way that their half-life is prolonged. So generally, these hormones would have half-lives of 20 minutes, 20 to 40 minutes. When they are glycosylated, 60 minutes. So there is advantage in glycosylation. And what we find about these 2 groups of hormones is that the peptides that are not glycosylated are secreted by cells that are acidophilic. They stain acidophilic when you use hematoxylin stain or when you use polychromatic stain. So they will stain like red, like pink, that is acidic. And we call them acidophilic cells or acidophils. And these acidophils will be somatotropes for growth hormone, they secrete growth hormone. They are corticotropes, they secrete ACTH, although even corticotropes do have a little bit of glycosylation activity. ACTH sometimes is glycosylated, but we usually group it among the non-glycosylated, the straight peptide. And then the third colony of cells in this group of peptides are the ones that secrete prolactin or the mammoth or lactotrope. So those are the 3. And then the ones that are secreted from basophilic cells, cells that stain blue. If you stain with the iodine, like glucose, iodine, the pituitary, and the pituitary, you find some areas, some cells that produce glycosylated peptides. And these are two classes of peptides. The thyrotropin or the thyrotropic, the thyroid stimulating hormone, TSH, and the gonadotropin releasing hormone, the gonadotropin stimulating, the gonadotropins, that is follicle stimulating hormone and luteinizing hormone. And in the male, luteinizing hormone is called interstitial cell stimulating hormone. So these three hormones, or these three tropic hormones, that is TSH, FSH, LH, are secreted from cells that stain basophilic. They are basophilic cells. Glycosylation continues in these cells. And these cells are thyrotropes that produce TSH and gonadotropes that produce gonadotropes. And then, of course, there are some other minor anterior pituitary hormones, like the ones that act on the skin pigment cells, on the melanocytes, and these are produced by, they are synthesized in the melanocyte producing cells or melanotrope, mainly the beta melanocyte, the beta melanocyte stimulating hormone, or beta MS. There's also alpha, but we will not talk much about alpha. A lot of alpha melanocyte stimulating hormone comes from intermediate lobe, from the molecule we talk about later called POMC, which is the main peptide produced by intermediate lobe. You can't see there because in man it is so insignificant, it is almost rudimentary. So we talk about it as a third lobe, but mainly anterior pituitary, we talk about anterior lobe and lobe. So these are the hormones of anterior pituitary. They are regulated by release hormones from the hypothalamus, and they release hormones to lower glands according to blood levels of the hormones. So both anterior pituitary and hypothalamus detect levels of growth hormone, or for that matter, IGF, or what are called the growth hormone factors. Those ones go and inhibit growth hormone. Even glucose levels detected in hypothalamus can inhibit or increase secretion of growth hormone by negative mechanism. So that is how growth hormone will be regulated. Then we come to thyroid stimulating hormone. It is released according to its regulation from TRH, that is thyrotropin release hormone from the hypothalamus, like we saw, but also negative by iodothyronine. The pituitary detects the levels of T3 in circulation in blood, and then it regulates release of TS accordingly. If T3 levels are high, then we get a reduction in TSH production. If T3 levels are low, then we increase TSH. For the reasons we shall see later about actions of TSH. because it stimulates more production of thyroxine. By the way, the word thyroxine really means T4, but T4 is a storage hormone. It is a hormone in circulation and in storage, but it is not the bioactive hormone. It does not have receptor. But peripherally, T4 is converted to T3, is removed one iodine by deiodization, and then it becomes T3 in target cells for it to become bioactive. But when you look at all the thyroxine, 98% of all the thyroxine is T4, but it is not bioactive. It is not received by receptors. It gives you an equilibrium so that in the tissues, when you need a little bit more thyroxine, it is converted from T4 to T3, and T3 is the one that gives activities that we shall talk about for T3. So that is how thyroxine or TSH release is regulated, both from TRH of hypothalamus and negative feedback mechanism of T3 in circulation. And then we come to ACTH, and we find ACTH is primarily regulated by corticotropin release hormone, CRH, from hypothalamus. So that when CRH rises, ACTH rises. And that high ACTH goes to adrenal cortex to increase the levels of cortisol. But it is also regulated by cortisol, by negative feedback mechanism, so that if there is more cortisol in circulation, it inhibits further release of ACTH. If cortisol levels are high, they inhibit release of ACTH. Now, in all these hormones of anterior pituitary, where we are talking about negative feedback mechanism, in terms of controlling the release, we talk about two loops. Or you find sometimes in your reading, you find there is what the short loop and the long loop of negative feedback. The long loop is the normal loop of detection from blood from circulation to anterior pituitary. So that, for example, cortisol is detected by anterior pituitary by corticotropes, and it reduces or it regulates release of ACT, both synthesis and release of ACT. And if we talk about gonadotropins, something like estrogen is detected by hypothalamus and by anterior pituitary. And anterior pituitary, it inhibits release of FSH. And if the levels are low, they increase the release of FSH. And indeed, this is one way that contraception works, by giving estrogen all the time, so that there's estrogen in blood all the time. Therefore, it suppresses follicle-stimulating hormone because the levels are not changing, and that means there will be no ovulation if the follicle-stimulating hormone is inhibited, is kept constant level. So that is the long loop, estrogen to FSH release. Now, there's something else we call a short loop. And short loop is between hypothalamus and anterior pituitary. So that the ACTH that is produced can also suppress or inhibit hypothalamic production of corticotropin release hormone, CRH. At the same time, the follicle-stimulating hormone that is produced in anterior pituitary can also be detected by hypothalamus through circulation, and it will inhibit further release of GnRH, gonadotropin release hormone. The same thing with thyroxine, that the TRH or thyrotropin release hormone can also be inhibited by TSH at the anterior pituitary. Short loop negative feedback mechanism refers to that circulatory compensatory mechanism between anterior pituitary and hypothalamus. The long loop is the normal, which is pituitary to circulation, pituitary hormones to the target hormones. That is, for example, the cortisol, the estrogen or other steroids, the T3, and growth hormone factors, IGF-1, that is insulin growth factor 1 or somatostatin. Those ones will also regulate the growth hormone release. So that is basically the way regulation of anterior pituitary hormones is done. And you remember we told you for prolactin, they are regulated by dopamine from hypothalamus. So hypothalamus is the dopamine, dopamine is the prolactin inhibiting factor, PIH, or prolactin inhibiting hormone. However, there is a prolactin stimulating hormone, a medium-sized peptide of 31 amino acids that may be in circulation but has not completely come into our liver. But you know, just like we didn't have a growth hormone release hormone, we used to just have growth hormone inhibiting hormone, which was dopamine. But now there is an established growth hormone release hormone, which is about the same size as the corticotropin release hormone, about 45 amino acids length. That means they are medium-sized peptides. And it is important to realize the chemistry of hypothalamic hormones and the chemistry of anterior pituitary hormones. Anterior pituitary hormones are polypeptides, are long polypeptides. And also the other polypeptides that are glycopeptides, glycosylated peptides, which are made of alpha and beta subunits. That means FSH, DSH, LH, they have alpha and beta subunits, just like insulin, and all alpha subunits are the same. Beta subunits are the ones that are different. They are the ones that give specificity. They are the ones that are detected by receptors, and the ones that are responsible for the actions of these hormones. So those are the two groups, hormones of anterior pituitary, straight peptides, and although they are not straight, most of them are folded, and the glycosylated. Pure peptides are growth hormone, prolactin, and ACTH, and melanocyte stimulating hormone. And all the fragments of POMC, and we'll talk about POMC later, an intermediate lobe hormone, which is a precursor of ACTH, is broken down in periphery to produce ACTH and other peptide hormones, epinephrines, endorphins, and other hormones that are active on the brain. So that was the group. And then I've told you about glycopeptides, TSH, and gonadotropins. They have a lot in common, and they may interact when it comes to risk. So basically, that is how anterior pituitary works. And this is the difference between anterior pituitary or adenohypophysis and posterior pituitary, which is neurohypophysis, where we see that posterior pituitary gets its hormones from hypothalamus. The hormones, the two hormones of posterior pituitary are synthesized in neurocenters, in nerve centers of hypothalamus around the supraoptic and preoptic area that is around the optic chiasma and along the paraventricular area or along on the side of the third ventricle. And these are nanopeptides and they behave like neurotransmitters, and they are neuropeptides, and they flow directly in the nerves from hypothalamus into posterior pituitary for storage.
I love it. Yeah.
And that means, whereas you can see clearly there, posterior pituitary release is through vascular arrangement, hypothalamic hypophysioportal system. Posterior pituitary release is directly by nerve secretion. Therefore, these two nanopeptides, ADH and oxytocin, are also neuropeptides, even when they are produced in other areas, like some areas of brain and in the enteric brain, in the gastrointestinal mucosa. They behave like neurotransmitters, usually inhibitory neurotransmitters. So that is the comparison between anterior pituitary and posterior pituitary. In between, you have intermediate lobe of pituitary that we will not discuss very much. In man, it is just a vestigial structure. It is a rudimentary structure, and it mainly produces one large polypeptide called POMC, pro-opiomelanocortin, of about 247 amino acids long. So it's very, and generally it is broken down by enzymes in periphery, in brain, defragmented and produce ACTH. It produces alpha melanocyte stimulating hormone. It produces beta enkephalins and endorphins. And many of these are neurotransmitters in the brain, especially on receptors of pain. That is why we say opio, because it is opiate receptors that usually are in MC as a molecule, and most of it. And so we find POMC in brain is also important as an inhibitor. And in fact, when we talk about the hunger center, the feeding center, we actually found that POMC inhibits hunger center. It inhibits feeding center. And this is because it acts on. And when you remember, one of the striking inhibitors at the hunger center are the opiate alkaloids and other opiates, things like cat, that is cocaine and in amphetamine, the transcription factor or transcription peptide, which inhibits hunger, which is a component of opiates, a component of pain, a component of amphetamine and other suppress hunger center, and they also suppress inhibit. And that is important about POMC, is important about it. Lobe means that POMC is released into circulation, and you can even get levels of POMC in blood, but peripheral tissues do not have receptors of POMC. It has no action peripherally, but it is fragmented by enzymes to give you ACTH and other smaller hormones in circulation. And that is how it comes on action. However, if you want to read more about POMC, if you want to read more about intermediate lobe, just read about intermediate lobe in amphibians. in lower organisms like amphibia and fish, millions, and you find that this is the area where color is controlled from skin pigment is controlled from intermediate lobe. In amphibia and those others, chameleons and others, where melanocyte activity is very important, you find that intermediate lobe of the pituitary produces melanophores and iridophores, which color to match environment and even the color of the eyes. That is, the iris usually shows a color. Usually we talk about black, other colors, and that is because of some small platelets called iridophores. And then on skin, the color changes is because of production of something called melanophores that can change right from brown to green to any color you want. That is intermediate lobe. We will not talk much more about intermediate lobe. I only want you to remember it produces POMC, a large polypeptide that peripherally has no receptors, but it is in circulation and it is usually fragmented to produce ACTH, produce melanocyte stimulating hormones and enkephalins and endorphins. The important thing about OMC, about lobe, which even in anatomy is hardly easy to see. It's not easily seen like the other two lobes. So that is how the pituitary works. Anterior pituitary with polypeptides, posterior pituitary with nanopeptides, 9 amino acid chains, which are vasopressin or and so now we'll talk about actions of different hormones. I want you to think about one, actions. What does the hormone do? 2, hormones that stimulate production and release of each of these hormones. 3, factors that inhibit release of these hormones or reduce production and release in case they are supposed to or inhibit their release. And 3, what are the results of overproduction? What happens in excess in these hormones? And 2, what happens in deficiency? What is the pathophysiology or disease factors in excesses and in deficiencies of these hormones, so that we start them one at a time. Already you can go down to the slide that shows the 6 hormones. Let's go down the slides, please. Yes. A bit more. Yes, that slide, you can look at it and make a summary of all these hormones, anterior pituitary, and then you, below that, in your own notes, you put conditions of excess and conditions of deficiency. So that, like I told you, we are dealing with 2 colonies of cells. 2 colonies of cells of anterior pituitary that produce 2 groups of hormones. The ones that are looking acidophilic, looking pink staining, are peptides. That means they are not glycosylated, they do not have a carbohydrate moiety. And those are the ACTH, growth hormone, and beta LPH. Beta LPH is a lipid section of ACTH that controls lipid metabolism, while ACTH controls glucose metabolism. So beta LPH is just like ACTH, but it controls lipid metabolism. They are, of course, not also the same size. ACTH is about 34 amino acids long. A peptide, beta LPH is about 81 amino acids long, and it is also a peptide. And LPH deals with free fats and storage fats, while ACTH deals with glucose, or rather carbohydrates, glucose and glycogen. That is what they regulate. Even if both of them have a lot of action on the insulin activity, but one of them is in charge of glycolytic pathways, the other one is lipid pathways. That is beta LPH and ACTH, and they are both produced from corticosteroids. And then, of course, the other acidophilic ones are the growth hormone and prolactin right at the end there. Then we have TSH, FSH, ICSH, and TSH. Those three are the glycopeptides. They are basophilic. They are produced by basophils. Sometimes we may have tumors, adenomas, that are only affecting the acidophilic cells. And so we call them adenomas of acidophils. And they will mainly show abnormalities by increased growth hormone and prolactin, so that you get increase in growth hormone, something we'll talk about as acromegaly. And then at the same time, they may give you high prolactin, which will give you galactorrhea, and they'll also give you gynecomastia, large breasts, even when one is a male, or you get lactation at the wrong time when you're not breastfeeding. Those are tumors of acidophil cells, adenomas of acidophil cells. Sometimes you find adenomas of basophil cells, and these ones will mainly cause high levels of gonadotropin, but they will also probably cause a little bit of hyperthyroidism, a little bit of increased TSH. Now, what you find is that these hormones are also tropic to the gland they activate. Tropic means they cause growth of that gland, the health of that gland, the circulation of that gland, and the nutrition of that gland. So even mitosis of cells of a given gland depends on the tropic action of each of these hormones. So for example, high TSH will cause thyroid gland to grow bigger, to have more circulation, to have more nutrients going into it. And so if TSH levels are high, then you get a large thyroid. And we'll talk about goiter later. So it can be just because there is high TSH, or it can be because of that there is not enough iodine, so there's not enough T3 to suppress TSH. So TSH rises. Find the same thing with TH. If we have too much ACTH, hypertrophy of adrenal cortex, adrenocortical hyperplasia. And because ACTH is tropic to the adrenal cortex. This is why we talk about tropic effects. These hormones are tropic. They are stimulating to the glands they act on. So let's go down the slides again so that we look at actions of growth hormone. Let's go to growth hormone. Let's go back because I think that is, you look at growth hormone later when you reach it. Yeah, let's a bit more up. Yeah. Yeah, one more up. Yeah. So as you can see, I told you to just organize your mind. Think about each particular hormone, what it does, what factors cause its release, and what factors inhibit its release, and what are conditions if we have excess production, and what is a condition if we have deficiency. So next, down. Yes, that is growth hormone. Growth hormone, because we have said it is tropic growth cells, it is facilitating, it is stimulating to growth cells. That is mucosal cells, epithelial cells, and any cells that are growing. So that is important in utero and important in infancy, but mainly not after that for general cells or somatic cells. But it continues to be important even in adults for maintenance of mucosa, epithelia. You know, epithelial cells are discriminating every minute and new ones are forming. That is growth. Mitosis and hyperplasia is a continuous process. Is that we always have replacement of cells, we have growth of cells, we have increase. For example, the cornea you woke up with this morning is not the cornea you sleep with at night. Most of the cells will have flaked out and new ones will have come. And this is function of growth hormone all the time, which is somatotropic function of growth hormone. But at the same time, growth hormone has a large action like insulin. It facilitates insulin activity at the cell membrane for entry of glucose into cells. So entry of glucose, entry of free fatty acids, entry of amino acids into cells is promoted by growth hormone. And that is, and even when it is inside the cell, it promotes converting those small units to large units so that glucose is polymerized into glycogen in cells for storage. And this glycogenesis is promoted by growth hormone. The same thing, free fatty acids are polymerized into fatty acid chains for storage. And this is action of growth hormone, or rather, the insulin is facilitated by growth hormone. And most important, amino acids are also made into peptides. They are made into organic tissue in the cells. And this buildup of amino acids to peptides is a very important process of growth. So that in muscles, in bones and cartilage and everywhere, we have got this new growth of amino acids to peptides. And this action of growth is called somatomedin action. To medins is to mediate, is to facilitate, is to promote. So somatomedins are fragments of growth hormone or actions of growth hormone that go towards building up. So that growth hormone does not always have to act as the whole hormone, because growth hormone is large. It's something like 191 amino acids long. It's a very long chain. But we find somatomedins are small fragments like 34, 36, or 45 amino acid segments that are part of growth hormone sequence, amino acid sequence. And they will bind to receptors and they will cause growth. And that is why they are called somatomedins. They are called growth factors. So that we have cartilage growth factor, fibroblast growth factor, bone growth factor. Sometimes those referred to as somatomedin C, and we have other somatomedins, or we call them insulin growth factor 1, insulin growth factor 2, insulin growth factor 3, and so forth. So these insulin growth factors, because they have insulin-like activity, they help small units, glucose, lipids, amino acids, to enter cells at the cell membrane. That means they promote insulin receptors at cell membrane, and then inside the cell, they promote this building up. They promote glycogenesis, they promote peptide synthesis, they promote fatty acid chains. And that is why growth hormone action is referred to as two things. One, somatotropin, somatomedin, and two, it is insulin-like activity. So that we shall see in deficiency, we shall have reduced growth and reduced insulin response. In its excess, we shall have increased growth. And since most areas do not have receptors for growth, most of this growth will be in extremities. The terminal parts of limbs, that is hands and feet, can grow. Probably jaws can grow, but you also find the tongue and the liver still have receptors for growth hormone. So when we have got excess growth hormone in the adult, these areas may grow. And we'll be talking about that soon, that in excess in utero and in infancy, we can have gigantism. We can have the whole body growing. But in adults, we have what is called acromegaly. It is only the extremities of the body that grow, that increasing. So that is growth hormone. Down a little, next slide. Okay, sawa. Before we come to thyroid stimulating hormone, let me just finish that categorization of excess growth hormone. Yes, excess growth hormone in utero and in infancy leads to gigantism, which is growth of the whole body but proportional growth. So the whole person becomes big, becomes giant. But when it happens in the adult, most of those areas have stopped growing. Our bone epiphyses have closed, skull has basically closed, and muscles do not now have the growth hormone receptors to grow. So only tips grow, that is acromegaly. So that you have got large hands, large feet, but the tongue and the liver also enlarge, so that we have hepatomegaly and colomegaly. And of course, treatment of that is just to deal with the growth hormone, to inhibit the growth hormone, or to look for the adenoma, because most times there is an anterior pituitary adenoma that is causing increased growth hormone production that is affecting somatotropes. However, we said somatotropes are in the same class as corticotropes and lactotropes. So something else that will increase in acromegaly is prolactin activity. So you might find gynecomastia in acromegaly. You might find enlarged breasts, and sometimes they may produce milk then in man, which is called galactorrhea, if they are producing milk at the wrong time. At the same time, you might find there's more production of ACTH. So in people with acromegaly, you would also expect probably diabetic effects, high production or high glucose in circulation because of increased ACTH and cortisol activity. You remember cortisol is a glucose, so they can also be there. So these are the problems hyperproduction of growth hormone, and they require treatment, and we require scans to make sure there is no adenoma in the anterior pituitary in acidophilic cells. This is the commonest outcome of acidophilic adenomas or acidophilic tumors. So next now to TSH. Yes, the next important axis from hypothalamus to pituitary to thyroid is this axis of hypothalamic hypophysio-thyroid action that ends up with production of thyroxine, of the hormone thyroxine. I have already told you most of the thyroxine, 98% of thyroxine is T4, but it is in circulation and storage. It does not have receptors, it does not have action. The important thing about T4, it is the one that is converted to T3 in target tissues when necessary. When we need to increase thyroxine, when we need to increase T3, we just iodinize T4. We remove one iodine from T4, we get triiodothyronine, which is T3, which is the one that is recognized by receptors, which is the one that has. Therefore, this will only happen in areas where the T3 is important, is necessary, like liver and muscle. But you find most cells need T3 because it is the one that promotes basal metabolic rate, the one that increases basal metabolic rate or the metabolism in the cells. For example, heat production, ATP breakdown, and entry of glucose into the cell, as we shall see about actions of. So next, so that the cells at the target tissues need to have a deiodizing enzyme to remove one iodine from T4. And we shall see this iodization, which is the opposite of what happens in the thyroid, which is iodination. In thyroid, what we do to make the thyroxine is we add iodine onto tyrosine, which is iodine tyrosinase activity, so that we add iodine onto tyrosine and we make diiodothyronine or T2, and then we make T4. But in the circulation, in the target tissues, we change T4 to T3. Next. Next slide, please. Next. Next. We need where there is thyroxine. The thyroid gland. There is, yeah. That is a thyroid gland. Let's see the one before that. Yes. You look at the thyroid gland, and I guess you all know the anatomy of thyroid gland, so we don't have to go back to that because you know the anatomy. But something else I'd like you to look at when you do the Googling, something you can enjoy instead of just looking at nice body figures and things at your luxury time, go and look at the way glands or endocrine organs are arranged in the body. When you now come to thyroid gland, you find we reach a point where the body starts separating right and left. Remember, in your body was one in the middle. Thalamus was one in the middle. Hypothalamus was one with an anterior and a posterior lobe, but there was no right and left. But it showed some nuclei on the right and some nuclei on the left. Some nuclei medial, some nuclei lateral. So it started lateralizing. But now when we come to the thyroid, we find like we have a right and a left thyroid. but they are joined so that we have a right lobe and a left lobe. It's one thyroid. And it is here that the other glands start now separating into two, right and left, so that we have two parathyroids, right and left, although they can even be four, so that we have two on the right and two on the left, two parathyroids. And then once you now go below that, the adrenal glands, you have a right adrenal and a left adrenal, which even look different. Below the adrenals, of course, we come to gonads, and you have two. You have right ovary and left ovary. Even when you come to right testes and left testes, they are even outside the body. So that one is on the right side of the body and another one on the left side of the body, completely different areas. So that is a very interesting thing to look at in the hierarchy of glands. As we come from up to down, we also get separation from right to left, and the higher ones being more in the middle. Just like I told you, as we come from hypothalamus down to pancreas, we start with small units. Some hormones are even just one amino acid, like prolactin. And then when we come to catecholamines, when we come to thyroid hormones, again, they are derivatives of tyrosine, one amino acid. And then when you are in the posterior pituitary, you have medium size peptides, nanopeptides, 9 amino acids. But in the anterior pituitary is where you start getting polypeptides. Polypeptides that are 191, 192 amino acids, that is growth hormone and lectin. And you even have 218 amino acids in TSH and gonadotropins, in the glycosylated amino acids, something they share with insulin, the size. And when we come to talk about hypothalamic polypeptides, we talk about POMC, which is about 247. And we'll even be talking about the inhibitor of hunger center, which is called leptin, which is also at 247 amino acids. So very long polypeptides. You find there is a relationship between the hierarchy of glands where they are and function. There is also a relationship between the size or category of the hormone and where it acts. And then we'll, of course, we talk about the peptide hormones and lipid hormones, and you already have that categories. Anyway, let's talk about the thyroid gland. Two lobes, but they are joined in the middle, and the two act as one thyroid hormone. And their main action is to produce thyroxine, which you have said. Thyroxine, T4 as production, and then T3 for action, for activity. So it is good we look at the process of synthesis. How do we synthesize from tyrosine? The basic unit, the precursor molecule is tyrosine. How do we move from tyrosine to T4, tetraiodothyronine? We move there by adding one iodine molecule at a time. One iodine molecule at one site at a time, so that we add one, then we add a second one, but we don't go on to add a third and a fourth. We combine the diiodotyrosines. We combine two of them, they become tetraiodothyronine. So we don't actually synthesize T3. T3 is produced by removing iodine from T4. So from T1 to T2, and then we jump straight to T4. We'll see that. So what is important about this thyroid synthesis is that the thyroid cells need to collect a lot of iodine into them. They have what is called the colloid. It's like a factory. Cells, the thyroid cells that make iodine are called colloid or C cells. So they concentrate a lot of iodine inside them so that they can then use tyrosine. They of course collect tyrosine also, or they collect tryptophan or phenylalanine, and tryptophan, phenylalanine can also be converted to tyrosine. If you look at the structure of the molecule, is about the same molecule, it's a phenylalanine molecule. So you collect a lot of iodine in the colloid, you collect a lot of tyrosine in the colloid, and now you can make your thyroxine. It's like bringing things into the, you bring the unga, you bring the sukuma wiki, you bring the salt. In that kitchen, you need sufurias. You need a skeleton of where to mix these things. And that skeleton in the colloid cells, in the cells of the thyroid, is a protein called thyroglobulin. A globulin called thyroglobulin. And thyroglobulin is both synthesized in the thyroid cells, but it is also absorbed from circulation. So the thyroglobulin that has been separated from thyroxine is recycled back into this. So you need 4 things in this colloid. You need tyrosine, you need iodine, and you need thyroglobulin, and then the enzymes that iodinate the tyrosine. So you need iodinases, the enzyme. One thing we can talk about the cell membrane of these thyroid cells is that there is a very high level of entry of iodine to colloid cells. They are pumped. Iodine is specifically pumped by carrier proteins. Iodine is absorbed into these cells almost 100 times more than it is absorbed in other cells of the body. So there is concentration, there is iodine concentration into the cells. So to prepare these cells to produce thyroxine, you need all those things. You need tyrosine, you need iodine, you need thyroglobulin, some of it made there, some other circulated into the cell, and you need, of course, the energy, the ATP, to be able to carry out the biochemical process in this factory, because this is like a factory. And that is why you need to look at synthesis of thyroxine in the next slide and see how the synthesis is done. And remember, I told you we add 1 iodine at a time to tyrosine, and we make diiodotyrosine. Then when we have now many units of diiodotyrosine, we put them together and make the triiodotyrosine. So that shows you the circulation, the arrangement of circulation into the thyroid gland. Thyroid arteries are very important blood vessels. You've done them in anatomy. I know you have even learned how to operate for them. And a lot of problems, a lot of times, the thyroid artery can easily be injured when you're having neck surgery. And this is one thing we worry about thyroid. Many times because of goiter, because of enlarged thyroid, and also thyroid adenomas, we do surgery, neck surgery, and many times we can hurt these thyroid arteries. But there's something more important that can be injured here as we approach or as we operate around the thyroid gland. And I'm sure many of you already know or you have read. What is the structure we fear most when you are cutting around the surface of this thyroid? What is the most drastic result? What can be injured in this neck surgery? Somebody unmute yourself and just tell us the word. What can be injured? Now, if nobody has talked in 1 minute, And I don't want to ask the class rep publicly. The structure that is feared, yes, very good. The structure that is feared most is recurrent laryngeal nerve. Recurrent laryngeal nerve lies on the surface of this thyroid, and it can easily be cut, it can be injured during neck surgery, during thyroid surgery, and recurrent laryngeal nerve goes to the larynx, and therefore it controls voice. It is important for voice. So once you injure it, you paralyze the larynx and you can easily lose your voice. And that is why thyroid surgery is very important. The other problem is this diagram emphasizes blood circulation. The thyroid surface is so well supplied with blood vessels, with arteries and arterioles, that one of the biggest problems, because you can see the arteries enter from every side, because this is only one face. We are only looking at a lateral view, not anteroposterior. So you're only seeing one surface, but you can see all. But this is how the blood vessels are arranged. This is how blood enters the thyroid. A lot of blood from very many sides. And therefore, the biggest problem of thyroid surgery is bleeding. It can be a lot of bleeding. And that is, it is one place in the whole body where before you do the surgery or during the surgery, you have to be very careful about bleeding. You have to control bleeding. And so when you read very old surgery, if you'll ever read it, because maybe now you won't need it yourself, but you need to read it, there is some preparation or some fluid that is prepared for surgeons that is called the Django juice. And Django juice is local anesthesia which has been mixed with adrenaline, so that the adrenaline innate causes constriction of the small arterioles to reduce bleeding. So that as you cut or before you cut, you infiltrate this area with local anesthesia, which has adrenaline in it. And this is the most famous site where you use Django juice, although it can be used in other areas. I'm not sure a lot of it is used now. Many other ways of controlling the bleeding, but it used to be a very useful thing. But for physiology, it really means that this is an emphasis on blood circulation. Rich blood into the thyroid and rich blood out of the thyroid. We shall see that thyroxine and cortisol are two of the most important hormones in the body, in that they have receptors in almost all cells of the body. Their action is all the time. It is not like where some hormones are only produced when necessary, or the peak is very high and the low is very low for a long time. Cortisol and thyroxine are needed all the time, because if you have to maintain basal body temperature, you have to maintain basal metabolic rate in all cells, you have to be producing thyroxine all the time. And that is why this rich blood network. And see it. So you study those slides at another time so that you can see the importance of circulation, the importance of intensity of activity in the thyroid. Let's go to the next, so that the next one, so that we discuss one. Oh, sorry, let's hold on to this one. So that we can actually appreciate what we have just been talking about. That if you stain the thyroid, no, the one you have just been showing us, this one. If you stain the thyroid gland with polychromatic stain, what do you notice? This gland has a lot of Golgi apparatus, it has a lot of mitochondria, but mainly Golgi apparatus. And it has a lot of concentration of iodine, so that when you stain it, these tissues take a lot of iodine. You can actually see, even after you have stained with iodine, glucose iodine, and you have cleaned, the whole place is blue. It shows you a lot of iodine in this cell. That if you look at 50% of the cell volume is made of iodine. And that means how important iodine entry is for thyroid cells. The follicles, or these follicular cells, are full of iodine. And that means there is iodine pump at the cell membrane, so that iodine is pumped in forcefully or actively. And this is why a lot of ATP is used here. And this is why we also have to have a lot of mitochondria here. And this is why we see that a lot of energy is used in these cells just to put iodine into the cell. This is what the thyroid does physiologically all the time. How would this also help us in medicine? We find that in treating thyroid tumors, because it is also possible to have thyroid, well, thyroid adenomas are common, but it is also possible to have thyroid carcinoma, that is cancer of the thyroid. And you find now to treat the cancer of thyroid, it would be useful to use this mechanism of iodine concentration. That in this case, you use it to deliver radioactivity. So that if you have thyroid cancer and we want to treat you, we treat you with radioactive iodine. And you will absorb a lot of iodine, a lot of radiation into the colloid cells, which will not happen in other cells of the body. So the cells of the neck around will be safe, even when you have concentration of radioactivity in the thyroid gland, in the colloid cells. And that way you can kill the cancer cells specifically or selectively in the thyroid without so much damaging the other cells. This is the important thing about this high absorption of iodine by active mechanisms. You go and read about iodine reabsorption and absorption in colloid, and you'll actually find we have two mechanisms. We have two pump mechanisms. One is to attract iodine into the cell. The other one is to recirculate iodine that has been released from tetraiodothyronine, so that that iodine is not lost, it's circulated back. So we have two mechanisms of iodine uptake. We have uptake 1 and uptake 2. And one uptake 1 is very specific by specific receptors. And uptake 2 depends on concentration gradients. So you read uptake 1, uptake 2 of iodine. So next, so this is what I told you about synthesis of iodine. This is inside the colloidal cells. The colloid is the fluid, is the cytoplasm inside these cells, the C cells. And you find what I told you. You need to bring in tyrosine. Sometimes it has been synthesized from tryptophan, from phenylalanine. So you get tyrosine into the colloid. You get a lot of iodine into the colloid. As you can see on the left side, is absorption of iodine. It has to be changed from molecular iodine to atomic or ionic iodine. And that is an important mechanism of making the iodine ionic. And then you go from up to down. And the first step I told you is you put one iodide on position 1 using iodotyrosinase, so that, or rather tyrosine iodinase. You put iodine on the tyrosine at position 1. That becomes monoiodotyrosine. And then you take the monoiodotyrosine and you add another iodine at position 3. So now you have a 3,5-diiodotyrosine. So the first one you put on position 5, the second on position 3. So you end up with 3,5-diiodotyrosine, or what we refer to as DIT. Now, after DIT, you do not go to DI3. You don't add another iodine. What you do now is you take 2 of these diiodotyrosines, and using the position number 4, you now put the 2 iodines together. And as you can see, you put a DIT and a DIT together. And because you have already changed the O in the middle, the O at position 4, the OH into an O, you actually are now dealing with alanine. You are dealing with iodoalanine rather than tyrosine. But when you put them together now, they are tetraiodothyronine, and that is T. So the summary is down there, that you have MIT plus DIT will give you an alanine iodothyronine, which is a T3, and a DIT and MIT will give you the same thing, which is like the T4. The positions are different. But in actual thyroid gland, we actually put DIT together with DIT and we make 4IT. We make T4. So this T4 is what goes into circulation, is what goes into storage, and is what will be changed in the tissues. Remove one iodine, you get T3, you get triiodotyrosine, and that is what will act. So this diagram is only summarizing what I told you, that you need iodine, you need tyrosine, and you need the thyroglobulin, the big skeleton, the big molecule that is there shaded purple and shaded blue on the other side, so that this goes like on is like a rail line that you move from top to bottom, and when you reach the bottom, it is detached, it goes off. The thyroglobulin is recirculated and used again. So this is basically what happens. And that is a synthesis of thyroxine. So when we talk about deficiencies or abnormalities of synthesis, you find the failure can be any of these, but the commonest failure is lack of enough iron. Just like any factory, like Mumias and where they were fighting yesterday, Mewani, you find the biggest problem is if you don't have enough sugar cane inside the factory. That is what causes problem. Even here, if you don't have enough iodine entering the cell, then you have a problem. You get hypothyroidism. If you have hypothyroidism, you don't have enough T3 in circulation, so you have nothing to inhibit TSH in the pituitary. So TSH levels go up, and because TSH is tropic to thyroid gland, the thyroid gland becomes large. It continues to enlarge because of the high TSH in circulation, and that is called a goiter, benign enlargement of the thyroid gland. Cause adenoma for any other reason of metaplasia can happen, but rare. Carcinoma also does happen, and that is malignancy. But the commonest cause of goiter, the commonest cause of enlargement of thyroid gland is low TSH, mainly caused by poor iodine, lack of iodine. If you are born around the time I was born, nobody would explain to you about goiter. Goiter was a very common problem around the country. Many middle-aged women and older women walked around with very large thyroids, sometimes only one lobe, one side, like a right side is large, left is not. Many people walked with goiter, with a large thyroid gland. And that is how polo neck got its popularity. They used to wear things around the neck, and that is why even when you find the necklaces that are now used by some of our pastoral friends, large necklaces colored covering the whole neck. One thing was to cover goiters. Goiter was very common because there was a lot of areas, especially highlands, where there was not enough iodine. Because of rains, iodine gets soaked down the soil and goes deeper, so it is not available. Many other places, because of erosion, their soils did not have enough iodine, so we didn't have enough iodine. Iodine is mainly dietary. We usually get iodine from diet, although as I've told you in these sentences, you also get a lot of recycled iodine from the body. And that is why in the world, and especially in East Africa, from late 60s, we started iodinizing our salt and other substances, so that all the salt now you get, all the salt you have, has to be added iodine, so it is iodinized. So now almost the whole population would have enough iodine. So goiter is becoming much more rare. And if you find goiter, look for other causes of reduced iodine. Maybe a problem with absorption or a problem with the active mechanism of entry of iodine into the cell, or look at the enzymes, the tyrosinase and the iodinase. Otherwise, that is the story of iodine insufficiency, goiter. And the two things we have worried about or looked after in public health, water and nutrition, is that everybody gets enough iodine in the country and everybody gets enough fluoride in the country, because you also remember the importance of fluoride in bone formation, especially in teeth. And that is why you find the physiology of iodine, the physiology of fluoride are very important when you talk about public. As far as TSH is concerned, this is how iodine and tyrosine are brought together to make thyroxine. This is how thyroxine is circulated and stored in the body, finally converted to E3 for action at the cells. Next, action at the target. Next, I think we are only going to finish thyroxine. Then the next session we meet, we'll now be talking about the cortex. We talk about the adrenal cortex. So I've already told you about production of thyroid hormones. You need thyroglobulin as the protein, as the skeleton or shell along which thyroxine will be made. Triiodothyronine or tetraiodothyronine will be made. And this thyroglobulin is recycled. That means when you finish, you release the thyroid, the thyroxine, and you leave the thyroglobulin to be used for another synthesis. So that one tyrosine and then a second tyrosine at position 3, and then you put two T's to the two MITs together, and they make T4. That is triiodothyronine. Next. Yes. That we have already talked about. And when we say that thyroxine is produced in the thyroid gland on the anterior part of the neck, we must also remember that the same gland on the sides, it has those two small glands attached. They are the size of a pea, PEA, the bean, the small round bean, the size of a pea, and these are the parathormones. These are the parathyroids, and they produce parathormone. But the thyroid gland itself has other cells other than colloid cells which produce calcitonin. And calcitonin does not work like thyroxine in raising basal metabolic rate and facilitating insulin action. Calcitonin is involved in calcium, phosphorus metabolism, bone mineralization, and bone growth. So that for putting calcium onto bone, we need calcitonin, and calcitonin is a different hormone from the thyroid gland, from different cells from thyroxine. And whereas thyroxine, we said, is a derivative of just one amino acid, tyrosine, calcitonin is actually a peptide. It's a medium-sized peptide of about 42 amino acids. And it occurs in two fragments, and both fragments attach to receptors, so that even the small fragment of calcium, which is called calcitonin, kama calcitonin imekatwa, calcitonin, which is about 28 amino acids, it will also have the same activity on this receptor for calcium increase and phosphorus. And the way you increase calcium in circulation, the way you decrease calcium in circulation is to put it back onto bone and to also reduce excretion at the kidney. Same thing with phosphorus. Calcitonin conserves calcium and conserves phosphorus at the kidney at excretion. It also facilitates absorption of calcium and phosphorus from the intestines, while parathormone does the opposite. It causes resorption of bone so that more calcium is added into circulation, so that when you can consider calcium in bone and cartilage as stored calcium, and it is molecular calcium. But when we need to mobilize it to increase ionic calcium, to increase calcium in circulation, then we use parathormone, which is produced by the parathyroid, which are small glands on top of the thyroid, on the surface of the thyroid. When we want to decrease calcium in circulation, to put more calcium onto bone and cartilage and other tissues, then we use calcitonin. So that calcitonin, calcium mobilization. The only relationship of these ones with the thyroxine is that they're all produced on the thyroid gland. And we'll leave it at that. You go and read about calcitonin, parathormone, and regulation of bone metabolism. Otherwise, for thyroid, very quickly, we talked about next. Yeah, we have already talked about actions of thyroxine. You go and read them so that you can understand what effects deficiency of thyroxine has, and that is called hypothyroidism. What effects hyperthyroidism has. Some of the widespread effects of thyroid hormones in the body are secondary to stimulation of oxygen consumption. So thyroid largely has calorigenic action. So it mobilizes use of energy by increasing oxidative process. You remember oxidative process happens in the mitochondria, but throughout our respiration, we are using oxygen to break down ATP to produce heat and energy. Now, this basometabolic function, this metabolism of oxygen and glucose and lipids to produce energy for the body is what thyroxine stimulates. So that we can say thyroxine accelerates metabolism. It is also important in growth and development. That is in all mammals, but now we are talking about mammal, growth and development. And that is why when you have hypothyroidism in childhood or utero, you actually get dwarfism, or you get a problem of stature, and that is called cretinism. The one that is due to thyroidism, cretinism. That means you don't grow tall and your limbs don't grow tall, but you find some tissues that don't depend on this thyroxine too much, like the tongue and the liver, they grow big, even if the rest of them not grown big. The reason why they are also in emphasis here on development is that if you have cretinism, you also get mental retardation, because the development of brain depends a lot on thyroxine because of course of metabolism. They help regulate lipid metabolism, I've told you, in the same way they regulate glucose. As you break down glucose for energy, you also break down lipids for energy. They increase absorption of carbohydrates from intestines, because if we are facilitating energy and ATP production and heat production, we also need to increase the raw material. We need to increase absorption of carbohydrates from the intestine. They also increase the dissociation of oxygen from hemoglobin by increasing 2,3-DPG. Because as you remember, 2,3-DPG in the red cells helps to keep an equilibrium with oxygen. When oxygen levels go down, 2,3-DPG's levels inside the red cells go up, and they release the oxygen they are carrying on to the hemoglobin, and they can also absorb from the hemoglobin. They give an equilibrium of oxygen to hemoglobin. Next. So that you can see thyroxine is important in all energy metabolism, in energy production, in basal metabolic rate in the body. And that is why thyroxine can also be misused as a drug of abuse in sport. Thyroxine and erythropoietin. Because what thyroxine does, erythropoietin also does in terms of release of oxygen from hemoglobin. Because hemoglobin oxygen dissociation. Next. So how does thyroxine act? It stimulates hypothalamus to release thyrotropin release factor, now called thyrotropin release hormone because it is an identified hormone, which stimulates anterior pituitary to produce TSH. And TSH stimulates thyroid gland to produce thyroxine and even to release thyroxine from the thyroglobulin. Now, as we shall see, go on, as we shall see, it increases this thyroxine production in 3 ways. Next, 3 ways. And one is by increasing, back to that one, because it was last. 3 ways. First is by increasing thyroglobulin concentrations in the colloid cells, both by synthesis and recycling of thyroglobulin. It increases entry of iodine into cells by active mechanism, like we said. It increases iodination of tyrosine, and it also increases the coupling of iodotyrosine to tetraiodotyrosine. And TSH even follows thyroxine outside the cell, and it increases removal of one iodine from T4 to make T3 by an enzyme called T4 iodine, T4 convertase, or T4 deiodinization, which is a T4 T3 convertase. So it increases conversion of T4 to T3 in circulation. So those are 4 things. It works on thyroglobulin, it works on iodine, it works on the enzyme for iodination, it works on T4, T3 conversion. So you can go down and see whether we have talked about the problems that may occur with thyroxine action. We have hyperthyroidism and we have hypothyroidism. Go on. Sorry. Yeah, just go back to that thyroid. I'm afraid the virus has removed some 3 slides. But the 3 slides are mainly about pathophysiology of the thyroid gland or deficiencies. Let's talk about deficiencies of thyroxine and oversecretion of thyroxine. We start with deficiencies of thyroxine and they lead to hypothyroidism. And because we have already seen the importance of thyroid is growth and development and the day-to-day energy output, basal metabolic rate. So when you have hypothyroidism, if it is very early in life or in utero, then you get a small stature syndrome that is called cretinism. A cretin is a small person whose body is not proportional. You find the body is small, but the head is not necessarily small. So if you look at the whole height from the top of the head to the toe, you find the center of gravity or the center of the body will not be at the umbilicus, it will be somewhere around the breast, around the nipples. And this person has a big head and smaller body. We find they also have a large tongue and large liver, hepatomegaly. All this is related to metabolism. We also find they have mental retardation. We'll not talk about many other things. You can check those by Googling. They'll also have cardiovascular institutions deficiencies, cardiovascular abnormalities. But what I want you to concentrate on is their small for is their small stature and their mental retardation and the disproportion of the. Why do you need to know that? It's because you differentiate it with dwarfism, which we talked about as a deficiency of growth hormone. Those ones will also be small stature, but the body will be proportional. That means the size of limbs, the size of head, position of neck, everything will be proportional like any person. And you also differentiate them from small stature that may be nutritional, which is called failure to thrive. Again, you find that person is also small, is proportional, but there are many other things we'll talk about in that nutritional dwarf. Otherwise, the word dwarf really refers to growth hormone insufficiency. So what else is going to happen to this person who have hypoglycemia? They have low energy. So they look lazy. They don't do things quickly. They don't think quickly. They don't move. They can sit there and not be bored. You find many of them like to work like in a kiosk or a store where they are selling something, selling slowly. Just pick this, give that, but many times they may not even notice when somebody walks away without paying. Many times they're also left with the change and somebody has to remind them. They are slow in what they do and they can persist for a long time. They can be in one position for a long time. The skin tends to be a little bit thick because we saw thyroid has a lot about liquid mobilization. And we'll find that sometimes their skin may be, in adults, the skin of limbs, especially legs, may be thickened with edema, and we call it that condition when somebody's like that and has hypothyroidism and mental slowing. Sometimes it's referred to as myxedema madness. Myxedema depression or myxedema madness. It means they have myxedema, they have got hard edema of their legs. So that they also have skin thickening. So that is hypothyroidism. Basically, short person who tends to be a little thick in the body and thick in the mind and a bit slow. And normally, they may not be able to appreciate being hot. So many times they're feeling cold. Now, what about hyperthyroidism? Of course, hypothyroidism, you have to deal with the cause. Is it iodine? So that you can give iodine, or is it TSH, or is it hypothalamic? The opposite is hyperthyroidism. And of course, hyperthyroidism, you all know the features. Because a lot of times I hear some of you talking about somebody being hyper, and that is actually what hyperthyroidism is, and somebody is hyper. They are very active, they are producing a lot of energy and using it, they are restless. In fact, even if you tell them to extend their hands straight, you find they have tremors. They have tremor at rest. Muscles are always active. They themselves are always active. The mind is hyperactive and a little bit flirting, moving from one to the other, unstable in a way. And of course, their moods are very labile. They'll change mood very fast and they are irritable. And important thing is heat intolerance. They have heat intolerance. Even when it is cold, their body may feel very hot. And when it is hot, their body may be feeling uncomfortable or cold. So they have problem with thermal regulation and appreciation of heat. They usually have high appetite, they eat a lot, but they don't grow fat. They eat a lot, but lose weight. Many hyperthyroidic people will be thin, or they will have lost weight over the time the hyperthyroid has come. And therefore, all these are things we see in hyperthyroidism, hypothyroidism, and the test that is normally done is simple. You just look at the levels of thyroxine in blood. You compare thyroxine levels with TSH levels, because as we have said, if somebody's T3 is high, then their TSH should be low. If somebody's TSH is low, then their T3 is low, is high, because it is inhibiting. But if you find somebody whose TSH is high and T3 is also high, it means they have a problem. They have hyperthyroidism, and probably it's because of a thyroid, is because of a pituitary adenoma, it's because of too much production of TSH. So the main test that is done in blood is to find out the ratio of T3, T4, and the ratio of thyrotoxin. Or if you have cut off the lecture.
It's already one. Sorry, some people getting tired.
So we just say the last sentence, that for investigations of thyroid function, we do thyroid function tests, which is the ratio of T3 to T4 and ratio of thyroxine to TSH. And the other thing, of course, you scan the thyroid itself. You do radioactive scanning, or you do normal scanning, especially with radioactive iodine, to see if there is increased activity, increased absorption of radioiodine. So we'll stop there. And the next time we meet, which is Wednesday, we'll talk about the adrenocortical, hypophysio adrenocortical axis. And that is what will bring us down to the function of cortex, steroids, and we'll spend quite a bit of time on steroid physiology. So please go and read that.